Okay, so let's talk about problem three. So the first thing I did, because there's a whole lot going on, was to draw a motion map. And so I actually started the motion map immediately after it got kicked, so the rocket is still being applied. So I didn't include the force from the kick, but I'm including the force from the rocket in this whole thing. So let's talk about the key for my motion map right here. A diamond will be the applied force from the rocket, which is a constant force of 10 newtons in the positive direction. The triangle will be the drag force, which will be opposing the direction of velocity. The acceleration will be the square, and that will be dependent on these two forces. And then you have velocity, which is, dependent on acceleration, and it's a circle. So I have negative is this direction, positive this direction. I start the car at the origin right here. And it because it got kicked, it has an initial velocity of negative 15 meters per second. So that's why it has the velocity vector right here. And then it's always going to have the constant force of 10 newtons from the rocket. So you have that right there. It's all across, always going to be there, as you can see. But the drag force is what actually changes. And so that's going to oppose velocity. So velocity's pretty high going in the negative direction. So drag force is going to be pretty high going in the positive direction. So because both of your forces are going in the positive direction, you have to have a positive net force and therefore a positive acceleration. So that's why we have it here. So since it's accelerating in the positive direction, it's going to slow down. So here's a smaller velocity vector than before. And now because it's a smaller velocity vector, you have a smaller drag force because there's less motion to oppose. And so, yeah, this gets smaller, but the applied force stays constant. And then eventually the car is going to go to a halt right here. So it's not moving here. However, it still has the applied force of 10 newtons from the rocket, so it still has a slight acceleration right there. And so it's going to start moving in the opposite direction. So now, this is actually pretty interesting. It's constant force of the 10 newtons from the rocket. It's starting out to move with a small velocity, and then you have the drag force that will oppose the velocity here. So it's the drag force has actually switched directions now that the velocity has switched directions. So acceleration vector will start out bigger and it will get smaller because the drag force is getting bigger while this stays constant. So the drag force will continue to get bigger actually until it reaches the same size as the vector from the applied force of 10 newtons, and these are actually drawn. They should be the same length right here and here. And so that way you have balanced forces, and then it's moving at a constant velocity. And so, yeah, the next step that I did after drawing the motion map was to draw what the graphs I thought might look like without drag force. So this is just with the applied force of the rockets. You're always going to have the positive force of 10 newtons. So your net force is always going to be 10 newtons. And then the acceleration, because it's based on net force, is going to look the same. It's going to be the same shape. So it's just constant acceleration. Then velocity, because the velocity will be increasing, but because acceleration is constant, the slope of the velocity will be constant because acceleration is the slope of velocity versus time. So there you go with that. And then the position graph, if you look, um, the velocity graph is negative, which means that the position, or I'm sorry, up until right here, the velocity graph is negative. So the position graph is going to be decreasing. However, it's also an increasing slope, so it'll be concave up the whole time. So it's decreasing then increasing as the velocity graph is negative and positive. So that's what I thought they'd look like before drag force. And now let's look at what it'll look like with drag force. So you have drag force. The equations on the front actually showed that drag force with a small relative velocity will be linear. And so I assume that these were pretty small relative velocities because you could get way faster. So I chose to make my drag force linear. So it starts out positive because the velocity is negative, and so it's opposing velocity. So it starts out positive, and then it decreases as the car slows down. So it decreases to a halt here, and this is T1. Oh, I'm sorry. I have two reference points. T1 is the time when it turns around, and T2 is the time when it reaches the terminal velocity. So T1 is when the drag force is zero because right here, there's no drag force when it's not moving. And then T2 is when the drag force equals the magnitude of the applied force. So I have negative 10 newtons because the applied force is a positive 10 newtons. So that's where it'll reach its constant velocity, and then it'll just flatten out and go at a constant, or and then the drag force will just stay constant from there. So then the net force, because net force is just the sum of all the forces, and you have a constant applied force of 10 newtons plus the drag force, I figured you just add 10 newtons to whatever the drag force is. So that basically shifts this entire graph up by 10 newtons. So instead, when it turns around, the net force will be 10 newtons instead of 0 right here. And then the net force will be 0 at when it reaches a terminal velocity because they're balancing each other out, and then it'll just continue to stay at 0. Then, because acceleration is based on net force, I made acceleration sort of the same shape as the net force. So yeah, that's just it right here. It's non-constant acceleration actually, but it has a constant slope right there. And then it'll just flatten out with 0 acceleration once it reaches constant velocity. So then now it gets a little bit trickier for the velocity and position graphs. The velocity, it starts out negative 15 meters per second, and then it is still increasing. Or wait, no, I'm sorry, it's not increasing. Velocity is moving closer to 0, so its magnitude is decreasing, but it's also decreasing at a decreasing rate, if that makes any sense. So it's, yeah, that's the reason I drew it like that. And then after, so the velocity hits 0 right there, and then it starts to increase, but because drag force is sort of changing, um, I have it still increasing like this, and then it'll hit a constant velocity as soon as drag force equals um, the applied force. So that's T2, where terminal velocity. And then, yeah, this part was really tricky, the position graph. So if you started at the origin, just because I started my motion map at the origin, you could start it anywhere you want. Um, you have both forces going the same direction, so you have the acceleration vector, but the acceleration vector is not constant, so it's not going to look quite as nice as this curve I drew. It should be a little bit more like it's hard to draw, but it sh- it shouldn't be quite a parabolic curve. It should be more looking like a cubic thing. And so the position slows until it stops moving. So here's T1 where it stops, and then it's going to move in the other direction. So it's increasing, 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 and then it gets to a constant velocity where the slope the slope of the position graph remains constant, and that's right here. So yeah, that's pretty much how I did my graphs and everything for question 3. Anyways, thanks for watching.